Okay, so today we'll change topics a bit and we'll start talking about continuum. So we're going to be talking about continuous random variables. Okay, so the main point that one has to do, think of this is now, again, okay, we're going to have a random variable, which is a function which is going from the sample space onto R, which is measurable. So what we need is the probability. So we need x inverse of an interval minus infinity up to any point A is in F for every A in R. Okay, so this is the definition of random variable. So the main difference between continuous random variables and discrete random variables is the following. The probability that x is equal to x is equal to 0 for every x in R. Okay, so the image of x is not a discrete set. Okay, so what are the examples of this? And then we'll give a definition. So the example of this would be, for instance, x is uniformly distributed in an interval AB. So again, this would be like saying that this variable is like a Bernoulli variable, a geometric variable, exponential variable. So this is an archetype of distribution. For a continuous random variable. Okay, and this symbolizes like picking a random number between A and B with uniform probability. So in this case, if we take, so we have the whole of R, let's say here, and we have A and B. So the distribution picks any number, any random number between A and B. So one of the things is picking this number and picking this number has exactly the same probability. The point that we should make is the following, that the probability that x, this notation, the probability that x is equal to c is equal to 0 for every c in AB. Okay, so what do I mean by this? So if you're picking a random number between A and B, if you choose this number here, C, the probability that you actually get that exact number is 0. So this is the difference between discrete random variables and continuous random variables. In the continuous random variables, the probability of getting an exact point will be actually equal to 0. And so what you can get is what is the probability of being in an interval, okay? So we cannot rely on the probability of points to figure out information. We need to deal with the probabilities of intervals. Okay, so let's try to make this a bit clearer. Okay, so we have the same picture. We take A, V, and perhaps let's try to take A to be equal to 0 and B to be equal to 1. So to make this a little bit less abstract. So if I pick a random number between 0 and 1, what is the probability that the number is less than 1/2? So the probability that the number is going to be less than 1/2 is going to be 1/2. So the probability that x is less than, so in this case, in the other case would be b plus a over 2. So the midpoint between b and a is here, is b plus a over 2. Then you would get all of this size. So you would get the size of this interval. So the size of this interval is 1/2 of the size of the interval from a to b. Okay, so the probability that x is less than b plus a over 2 is going to be the size, so the size of the interval a to b plus a over 2 over the size of the interval AB. So what I'm saying is the probability that you are less than b plus a over 2 is going to be the size of this interval over the size of this of the bigger interval. But if you choose exactly b plus a over 2, this is half of the size of the other interval. So in general, if you want to figure out what is the probability, so in general, if we want to figure out the probability that x is in a size A, this would be the size of A intersection the interval AB over the size of AB. Okay, so this has to do with like this is a similar interpretation. This is a similar interpretation to uniform counting. Okay, so this is when you have in the discrete case the probability that x is equal to x is equal to 1 over the size of the sample space. So let's say 1 over the size of the image of x for every x in the image of x. Then what you would get is the probability that x is in A is going to be the size. So it's going to be the size of A intersection the image of x over the size of the image of x. Okay, so this is the discrete analog of this continuous thing. So in general, so I'm saying the size of A over intersection AB over the size of AB. This can be seen in terms of the density function. Okay, so this formula can be obtained by the density function. So what is it in this case? So so let's write a definition now. Definition, random variable x is continuous if there exists a function f from R to 0 infinity such that the probability of x less or equal than x is exactly equal to the integral from minus infinity to x of f of y dy, and this is for every x in R. Okay, so this this is f the little f is called the density function. F is called the density function of x. And in general, we can denote it as like f of little x to have the dependence on the random variable. Okay, so the cumulative probability function for x, which is what we were before denoting by fx at x, can be written as a definite integral from minus infinity to the point where you are evaluating of f of x. Okay, so what we have from the previous things is that the derivative f of x prime is equal to little f of x. Okay, so a random variable, so a remark. So the remark would be this: f x prime is equal to little fx, and a random variable is continuous when fx, when fx, its cumulative distribution is differentiable. Okay, and so a way that we can calculate little f of x is by taking the derivative of the cumulative distribution. So if we have access to the cumulative distribution, we can calculate little f of x. Okay, so going back to the example. So going back to the example, so x is uniform between A and B. Then this would mean that little f of x at a given x is equal to 0 if x is not in AB, and is equal to 1 over the size of the interval. So this is size of the interval if x is in AB. So what does this mean? And I mean, we can even just check what is this probability for this particular thing. So let's say that we have the interval, so the picture we had before. So we have A and B, and here we have the points C and D. And now we want to calculate the probability that x is in C, comma D. Okay, so the probability that x is in C, comma D is going to be equal to the probability that x is less or equal than D. So this would be the probability that you're all the way here, minus the probability that x is less or equal than C. Okay? So you take the probability of your random variable being any number less than D, and then you subtract the probability that you are any number less than C. Okay, so the probability that you are between this interval is going to be the difference of these two probabilities, and this thing here is going to be the integral from minus infinity to D of f of x, let's put that x dx, minus the integral from minus infinity to C of the density function f of x dx. And if you put these two things together by these probability things, this is by the integral properties. This is the integral from C to D of f of x little dx. But now this thing here, as we said, for this f of x is 1 over b minus a if the x is between a and b. So it would change it, it would be a big difference if this interval CD is contained between a, b, or if this interval CD is not contained between a and b. So if the interval CD is not contained between C and D, the probability that you obtain a number in this interval would be 0. Okay, so this f of x has to be with an indicator that x is between a and b. Okay, so this is just equal to the integral from C to D of the indicator that x is in AB over b minus a dx. Okay, so the only dependence on x is through this indicator, which is taking care of this. And so this would be equal to the size of the intersection CD intersection A, B over the size of AB. Okay, and so this is, if you have access to the density function f, this is how you figure out what is the probability that your random variable is in a particular interval. So the way to check if your random variable is a particular interval, you can just integrate your density function in this appropriate interval. Okay, so in this particular way, we regain the same rule as before, that the probability that x is in a particular set A is going to be the size of A intersection AB over the size of A comma B of the interval AB, which is this formula here. So this would be D minus C over B minus A. This equality is if CD is a subset of AB. Okay, so this is an example. So this is perhaps the simplest example of a uniform random variable. So I guess I'll make this comment just so that. So let's say that x, I think I've said this a couple of times, but let's repeat it one more time. So let's say that x is uniform between 0 and 1. Then what we said is that x equals to q, so the probability that x is equal to q is equal to 0 for every q in 0, 1. Okay, so the probability of being exactly one number is going to be 0. Moreover, the probability that x is equal to qi, the union of I equals to 1 up to infinity of x is equal to qi, is going to be equal to the sum from I equals to 1. So again, here I guess I guess I would put like just the sum up to a finite value of n. So this is exactly equal to the sum of from I equals to 1 up to n of the probability that x is equal to qi, which is equal to 0. So by taking limits, we obtain that the probability that the union from I equals to 1 up to infinity of x equals to qi is equal to 0. Okay, so if we take, in particular, between the 0 and 1, we take a dense we take a countable and dense sequence of qi. So in particular, the probability that you land on this set is equal to 0. Okay, so in particular, the probability of landing in on, let's say, I think that the proposition is correct. In particular, the probability of landing on a rational number is 0. Okay, so because q is equal to the union from I equals to 1 up to infinity of qi. Okay, so this is what I'm saying is rational numbers are countable. So rational numbers are countable. So in particular, if I take an infinite, if I take a countable union of numbers, I can get the rational numbers, which implies that the probability, this thing here, implies that the probability that x is in Q is equal to 0. So the probability of landing into a rational number is 0. So in particular, this implies, okay, of course, it's an if and only if, the probability that x is in 0, 1 set minus q is equal to 1. So with probability 1, you will land in an irrational number. Okay, so this was part of your test, so I just wanted to go over it for some people that perhaps had not completely gotten it. Anyways, okay, so the point is that you have to get rid of the ideas of like sets of probability 1 can actually, the fact that x is equal to a rational number is plausible. It could be that x actually takes the value of a rational number, but this will be an event that happens with probability 0, okay? So it's impossible. All right. So, so let's look at a couple of properties. Properties of density functions. Okay, if x has density function fx from R to 0 infinity, then the first property is that the integral from minus infinity to infinity of fx dx is equal to 1. And the second one would be that the probability that x is equal to x is equal to 0 for every x in R, and C, the probability that C is less or equal than x, which is less or equal than d, is equal to the integral from C to d of f of x dx. Okay, so these are the things that we've been discussing now. So this in particular follows from the previous argument. So what we're saying is the probability that x is less or equal than x is, let's call it z. The probability that x is less than c is the integral from minus infinity to c of f of x dx. And now if we take the limit when c goes to plus infinity, the probability that x is less or equal than c has to be equal to 1. This is by the continuity of probability. This by the continuity of probability, and this implies that this is equal to minus infinity to infinity of f of x dx. Okay, so maybe just do another example in terms of area. So example, so we throw a dart on a target. Okay, so we throw a dart on a target. So here we would have like so we have the unit circle. And basically what we're saying is, so we have our sample space, which is the unit circle, and we say that any point in the unit circle can be an acceptable dart position, and we throw a dart on a target which has uniform distribution. On the target, which is the unit disk. Okay, so the probability. So if we take an area A here, so let A be a subset of the target. Then the probability that the dart is in A is going to be equal to the area of A over the area of the unit disk. Or let's call it area of target. So in particular, if we want to calculate what is the probability that the dart will land in a particular spot, so this is similar to the example that we were seeing before. The probability that dart lands in a specific spot is 0, but the probability that it lands in a particular area will be given with respect of the normalization of this area with respect of the area of the whole target. Okay, so what would be a random variable? So we can consider the random variable. So we can consider the random variable which tells you the distance to the origin. So we can consider the random variable, let's call it x, which tells you the distance of the origin, and the random variable y, which tells you, so let's call them differently. Let's call this capital R, which tells you the distance from the origin, and the random variable, let's call it theta, which tells you the angle. Okay, so basically r theta are the polar coordinates of a point in the unit disk. Okay, so this would be r omega theta omega. So r and theta are going from the unit disk onto r, which basically saying r of omega is going to be omega 1 squared plus omega 2 squared square root, and theta of omega is going to be, what is it, the tan inverse of omega 2 over omega 1 or something like that. Okay, and you have to basically normalize this between other things. So what I'm trying to say here, so if we take the unit disk, and we take a point omega. We take any random point omega in the unit disk. Then the polar coordinates of this guy are going to be r for that value, and then theta. This is r of omega, this is omega, and this is theta of omega. Okay, these are functions. R and theta are functions that are going from the sample space onto R, and they are measurable if we take the right notion of events. Okay, so in this case, we could calculate. So first of all, if we look at the angles, there is rotational symmetry. There is a rotational symmetry. What I'm trying to say is that whenever you rotate your target, you still get the same target. So the angles that you are going to get are independent of these rotations. Okay? So then the distribution, therefore, the distribution of angles is independent of rotations. Okay, so theta is something that is going from d to 0 to pi, and you can do it open and close. And what I'm saying is, whenever you rotate this, the angles you would like have to have them modding out. The distribution of theta of angles is independent of rotations. Okay, and you can actually show that the only the unique shift invariant density on an interval is, so shift invariant, I guess, would be translation invariant. Density on an interval is the Lebesgue measure. So in this case, what I'm trying to say is that if you look at the only thing that is independent by rotations in these kind of things, we could actually make this a little bit more formal. So what we're saying is that theta is going to be uniform with values 0 to pi. Okay, so, and this is something that you can see just from the symmetry, because whenever you rotate, you get always the same thing, then it should be independent of which angles you're getting. Okay, so then what I'm trying to say is that, yeah, this needs to be uniform just by the symmetry. Okay, so this is for the angle and for the radius. For the radius, we can calculate what is the probability that the random variable r is less or equal than little r. So here it would be the probability of this is going to be the area of the disk of the ball of center 0 and radius r over the area of the ball of center 0 and radius 1. Okay, so what you get here is this is 2 pi r squared over 2 pi, and of course this is r positive, over 2 pi. So this is just equal to r squared. So in particular, this can be written as the integral from minus infinity to r of the integral of 2, let's call it u, times the indicator of u bigger or equal than 0, du. Okay, so what I'm trying to say is that the density function for my random variable r is going to be 2u times the indicator of u bigger than 0. So what I'm saying is fr, the density function, is equal to this formula, this function right here, which is going to be 2u if u is positive, and it's going to be 0 if u. So again, I need to be careful. This is between r bigger than 0 and r less than 1. So this would be 0 less or equal than u, less or equal than 1, and is equal to 0 otherwise. Okay, and here I will have the indicator of 1 bigger or equal than u, bigger or equal than 0. Okay, so just to make sure that you understand what I'm trying to say. So I have the unit ball here, and now I want to say what is the probability that the radius of the point I have gotten is less than little r. So then what is the set of r less than r? Okay, so if this is little r, this is the set r less or equal than r, than little r. So in particular, if I want to calculate what is the probability that my random variable r is less than little r, I have to calculate the area of this set and divide it by the area of the full set. Okay, so the probability that my dart hits here is going to be this ratio, which I can just calculate to be r squared. In particular, what we said is that okay, so this is my cumulative distribution function, which is fr of little r. And so then what we are doing is to calculate the density function, little f of r, fr prime is little f of r at r. Okay, so differentiating this thing, we get exactly f of r. Okay, so we take r squared, we differentiate, and this is just equal to r. This is r squared prime. Okay, and this is the way that you can get distribution functions which are a little bit more complicated than uniform. Okay, so the angle is uniform, the distribution, and the other thing that I was, so the distribution for f theta is going to be equal to 1 over 2 pi if x is in 0 to pi, and it's going to be 0 otherwise. Okay, so this is the uniform distribution between 0 and 2 pi. Okay, just to remind you a bit of the things that we are going to want to do with this thing. So we have similar as before. We have the notion of independence. And here I think, I don't remember how I originally talked about this in the class a couple of weeks ago, but so let's put this in the next page. Independence. For discrete functions, we needed to check the probability that x is equal to I, comma, probability that y is equal to j is equal to the probability that x is equal to I times the probability that y is equal to j. Okay, so this is independence for discrete random variables. Now, for continuum random variables, we cannot check this because the value of the probability that x is an exact point is actually not going to be well defined. I mean, it's well defined, it's equal to 0, but it's not going to give you much information about your random variable. So what we need to check, what we need to check is that the probability, so x and y continuous random variables are independent if the probability that x is less or equal than little x intersection the probability that y is less or equal than little y is equal to the product of these probabilities. I think originally I gave the definition like this, and then you can check for discrete random variables that this is equivalent to that. Anyways, for continuum random variables, this is the definition, okay? So this is the definition for continuous random variables. Okay, so similarly, and I think this I had looked at a bit. So, theorem. If x and y are independent, then g of x and h of y are independent for any continuous functions g and y. Okay, so I proved this theorem before, but I guess so morally the idea of doing having to take for any continuous function g and h. So the thing is, one of the things that we should realize of this definition here is that, so a further property of independence. So one of the further properties of independence is the following. So let's try to write the following. So what is the probability that x is in AV intersection the probability that y is in CD, okay? So now the point is that this can be written as a union, okay? So as a difference. Similarly to what we did here, the probability that x is between CD is the probability that x is less than D minus the probability that x is less than C. So here we could write this as this is equal, by the law of total probability, the probability that x is less than b intersection y is in CD minus the probability that x is less or equal than a, y is in CD. Okay, so this is just to try to bring this intersection of events as sums of things that look like this. So we can use the notion of independence to actually get the product of these probabilities. Okay, so this is the probability of x less or equal than b times this intersection this set. But again, this is equal, so the probability that y, we can use the law total probability that said this is less or equal than the probability, this is equal to the probability that x is less or equal than b intersection y is less or equal than d minus the probability that x is less or equal than b, comma, y is less or equal than c, and similarly for this term, minus the probability that x is less than a, comma, y is less than d, plus the probability that x is less than a, y is less than c. So, so what was the point of doing this thing? So now, if x, comma y are independent, then the probability, so if x and y are independent, what I can say is that x less or equal than x and y less or equal than y, which are all of these sets that I have decomposed my probability into, can be written as a multiplication. Okay? If x and y are independent, then the probability that x is in AV intersection y is in CD is going to be equal to the probability that x is less or equal than b times the probability that y is less or equal than d minus the probability that x is less or equal than b times the probability that y is less or equal than c minus the probability that x is less or equal than a times the probability that y is less or equal than d plus the probability that x is less than a intersection y is less than c times the probability y is less than c. Okay, but now if you realize this is a perfect multiplication of these numbers. This is just equal to the probability of x less or equal than b minus the probability that x is less or equal than a times the probability that y is less or equal than d minus the probability that y is less or equal than c. But this thing here is the probability that x is in AV, and this thing here is the probability that y is in CD. So in particular, what we have seen is that the probability that x is in a set intersection y is in another set, when x and y are independent, this is exactly equal to the product of the probability that x is in this set and y is in this set, okay? And this generalizes for any measurable, for any set A, comma B. So the probability that X is in A, Y is in B, is equal to the probability that X is in A times the probability that Y is in B. Okay, and this equality is if X, comma Y independent. Okay, so I guess sometimes the definition of independence is a little confusing, but the point is that this is the minimal definition that you can give for independence, which then implies what you want, is that the X and Y are independent if the probability that X is in a particular set is the multiplication and Y is in another particular set is the multiplication of the probabilities that each one is in a specific set. So morally, whatever Y does not affect the values of X. Okay, so what did I wanted to say this? Because the proof of this theorem, which we had written before, so the proof of this theorem is we now need to look at the probability that G of X is in a set A, comma, the probability that H of Y is in a set V. And now this is going to be equal to the probability of X is in the set which is the inverse. So this is the inverse in terms of set, G inverse of A, comma, Y in the H inverse of B. And now the point is that this is a new set. This is a set C. This is a set D. If X and Y are, if X, comma, Y are independent, this is equal to the probability that X is in C or G inverse A times the probability that Y is in H inverse B, which is, again, is just the probability that G of X is in A times the probability that H of Y is in B. Okay, so once you realize that this generalizes this property, okay, this is an if and only if, then you can just check this theorem in just this specific case. The point is that to do this, you have to basically sum. You have to sum over disjoint intervals. Okay, I'm not going to follow this proof, but you have to be a little careful of how to structure this proof. Okay, so what else is there? So morally, what this class has been is to try to get you more used to continuous random variables. So in particular, we are going to introduce the same notions as we had for discrete random variables. So in particular, we can define the expected value. Okay, so definition. The expected value of random variable X with density f of X is e of x is just the integral from minus infinity to infinity of the integral of little x against the density function fxx dx. Okay, when the integral exists. Okay, so what does it mean that the integral exists? So it means that this has to be absolutely convergent. So in particular, we need, so the integral exists, that is to say, the integral from minus infinity to infinity of the absolute value of x times fx little x dx is finite. Okay, so let's just to try to make sense of this. So let's do a couple of examples. So what is the expected value of x which is uniform with AB? Okay, so again, this is some question that you can consider with symmetry. So in particular, let's consider the midpoint, which would be a plus b over 2. So the idea is that the expected value of x will be the midpoint because it's as likely that you are over this point that you are under this point. Okay, so the most likely, it's not that the most likely outcome is this, but the point is that on average, you are going to get something that is close to that. Okay, so most of the interval, the point that is closest to every point in the interval is going to be a plus b over 2. Okay, so let's take the expectation of x. This is the integral from minus infinity to infinity of little x times the density function, which in this case is just minus infinity to infinity of x times the indicator of x in AV over b minus a dx. So this is the integral from AV of x over b minus a, and this is going to be b squared minus a squared with a 1/2 in front over b minus a, which is just b plus a over 2. Okay, so this is the expected value of the uniform, which as we say is a plus b over 2. And then let's look at r, which is the random variable that we were looking at before. So f of r is equal to 2r if r is between 1 and 0 and is 0 otherwise. So what is the expected value of r is equal to the integral from minus infinity to infinity of, let's call it r, fx, f capital R of little r dr, which is just the integral from 0 to 1 of 2r squared dr, which is equal to 2/3. Okay, so if you look at this guy, this might be a little harder to realize. So if you look at the radius of how much you're saying, is you're saying that morally around a radius 2/3, so not 1/2 but a radius 2/3, is the most likely outcome for R. So if you realize this is not the same case in which you have a uniform distribution. The distribution between 0 and 1, so the distribution of R between 0 and 1 grows with R, okay? So because it grows with R, it's more likely that the value that you are going to end up is closer to 1. So we expect R to be closer to 1 than to 0. Okay, so what are the properties? Of the expected value. So they're really similar to the one for the discrete case. So if x is positive, so the image of your random variable is positive, then the expectation of x is positive. The second one is if, the expectation linearity, so the expectation of ax plus by plus c is just going to be equal to a times the expectation of x plus b times the expectation of y plus c. Okay, and this is what I call linearity. So what I'm saying is if you take a linear function of the random variables, then you get the same linear function applied to the expectation. What other thing we get? Similarly, we get that if x and y are independent, then we get that the expectation of x times y is the expectation of x times the expectation of y, which has to do with the correlations that we'll see in a second. And finally, what are we have? So if we have a function g from R to R, which is continuous, it doesn't need to be continuous, but continuous is a minimal thing to ask, is that the expectation of g of x, okay, so this is a random variable which is composed with this function g, is going to be the integral from minus infinity to infinity of the function applied to little x times the density f of x dx. Okay, so we did this for discrete random variables, but the point is you can do it also for continuous random variables and get the same expression here. So if you want to calculate what is this function here, you can look at this thing here. All right. So similarly, just to define variance, okay, so similarly, to the discrete case. So I'm not doing these proofs, but the idea is that you can go back to the proof for the discrete random variables, and you just need to be a bit careful with how you use the density functions and these kind of things to actually prove the exact same things. So I'm not going to do it, but it's an exercise you can look into. So similar to the discrete case, we can define the variance. So we can define the variance. So the variance of x is going to be the expectation of x minus e of x squared, which again, by linearity, is equal to the difference between x squared, the expectation of x squared, and the expectation of x squared. Okay, and this again satisfies the same properties as the expected value as it would satisfy for the case of discrete variables. We'll see them in following classes. So another thing is the inequalities. Markov and Chebyshev. And Chebyshev still apply because the proof is the same proof as before, in which we have that the probability that x is bigger or equal than a is less or equal than the expected value of x over a for x which is positive, for a random variable that is positive. Okay, this is Markov's inequality. And the similar Chebyshev is that the probability that x minus e of x in absolute value is bigger than a, this is less or equal than the variance of x over a squared. Okay, and this has the same proof as in the discrete case. Okay, so next class we'll be looking at is in some particular distributions. So similarly to how we saw in the discrete random variable case, we saw the Bernoulli and geometric and similar other types of distribution. We're going to see an exponential distribution in the continuous case, and we're going to be starting to look at the case of Gaussian distributions, which is really important for the theory later on.